Okay, so let's take a little while. Give me the products to these two. Okay, let's go ahead and take a look. Okay, so in the first one, we got a Diels-Alder reaction. The diene is symmetric, so we don't have to worry about regioselectivity as far as up and down, right? So we can put these together, it's symmetric. But whenever this does come together, I'm going to end up with a two-ring system like this, right? And that means that over here, I want to make sure that this is endo. Okay. Now, where the endo comes from is that whenever these come together, right, you have the choice of this transition state or this transition state. Okay. Because of the interactions between these p orbitals and that p orbital there, right, this is going to be favored. This results in the endo right, with the carbonyl going down towards the inside. This one, which is not favored, right, results in the exo. Okay, so one of the stereochemistry controls in a Diels-Alder is this endo versus exo. So endo is favored over the exo, and the reason for that is this pi overlap of that carbonyl with the backside here. Okay, over here, this is out here, it's not anywhere near there. There is no stabilization of that transition state. Questions about this one? Yes, ma'am. Yeah, I mean, one way to look at it is you could draw it this way, right? So that part of it is kind of coming out at you, right? So you could see that sometimes in drawing programs, they won't go as bold as you would see, but you'll see a little bit of bold. If this helps you, sometimes when you're staring at these, they'll go in and out. Okay, if that occurs to you, just make one side darker than the other, and it'll help you from getting that kind of optical illusion effect when you're staring at these. As we talked about last time, that you can also draw these, right, as flat, so your perspective is coming from the top, but even in that perspective, right, we would want the group underneath. We'd want the group down, okay? Okay, questions about these? Okay. Let's look at the other one. The other one is a Birch reduction. Okay, so a Birch reduction is going to take, right, a benzene to this isolated diene. But the question is if I have a group attached, is it going to be adjacent or not adjacent to that double bond? And in this case, it's not going to be adjacent, okay? And for that, we need to look at the transition state to explain that. All right, so here we get the isolated, but now this group is not attached to that. And the reason for that is that with that electron withdrawing group there, that one of the possibilities in the transition state is this radical with the negative, right? Okay. So this is and if that negative is on something that's an electron withdrawing group, right? What happens is that negative can be delocalized to that ring, to that carbonyl, right? So therefore, that's going to stabilize that transition state. So if it's electron withdrawing, I'm going to want it in this position, which means the two isolateds are on the side and not where that's attached. The inverse of that is if I had, let's say, a methyl group. If I had this, right, this is an electron donating group, right? It can give electron density to the ring. And what does that do to the negative? This destabilizes it. So in these groups, what we want to see is not next to it. What we want to see is adjacent. Right? Because then we don't have that destabilization of increasing the electron density. So electron withdrawing groups stabilize that, and that's why we get this structure, right? So if that's an electron withdrawing group, we want the isolated groups not attached to the same carbon as electron withdrawing group. And if it is an electron donating group, then we want the carbonyl on that, so it'll destabilize that negative. Yes, sir. That's the inductive, but you also have resonance, and resonance is more powerful than inductive. So if we think about carbonyls, they have a weak inductive, but they have a solid resonance. So carbonyls, nitro groups, sulfonates, all of those have potential resonance that I can take that negative charge and put it out on the ring. So it's pulling electron density away from that ring. So if my intermediate is negative, that's going to actually stabilize it. If my intermediate is positive, like electrophilic aromatic substitution, then pulling that electron density is going to deactivate. So you're not going to know what the transition state is. Things like carbonyl, things like oxygen and carbon, not carbonyls, but oxygens, can donate electrons back to that ring, and that's going to stabilize a positive and destabilize a negative. So what we have here is we have a destabilization of a negative by an electron withdrawing group. So, and you'll see some today, but, common electron withdrawing groups, are your carbonyls, right? Your nitros. And then of course your carbonyls, that's a lot of different things, right? Your sulfonates, right? And then your electron donating groups, are things like the lone pair R, the nitrogen has the lone pair, right? And then your alkyls, right? And so the top row would be not adjacent to the double bond in a birch. The bottom row would be adjacent to the double bond in the birch. Okay. Does that help answer those questions? Okay. So whether an electron withdrawing group is an activator or deactivator depends on the mechanism. In a birch reduction, we're going through a negative process. So an electron donating group is a deactivator, right? So I don't want it directly next to the negative. But in a birch, the electron withdrawing group is an activator. So I do want it directly next to wherever that negative would be. Okay. Now that's birch. Birch is negative. What happens when we go to electrophilic aromatic substitutions? Are we dealing with negatives in the ring, or are we dealing with positives? We're dealing with positives. So it's important to know what you're dealing with to determine how those groups are going to activate and deactivate. Okay. So the quiz starts today. You got 15 minutes. It's just 5 questions, 2 points each question. There's a few of you that I still need to give you extra time. Give me 15, 20 minutes after class and I'll give you extra time. We had some emergencies in the office this morning, and it'll be open till 10 o'clock, okay? It will not have the drawing like the Chem 101. It's just multiple choice type questions, okay? All right. Okay, so let's look activation, deactivation. Let's remember what we talked about on Tuesday, which was the methyl group. And let's go ahead and put it at the top. Methyl group here. Right, and if I did we see that we get a 1 to 2 ratio, or sorry, a 2 to 1 ratio between these two, right? But we also then get a trace of the meta. Okay. And then on this one, what we saw is that if we were adding this nitro group here, that we ended up with this positive, and that we could delocalize that positive over to the methyl group. And that stabilized. So that stabilized our functionality, right? Which means it activated it. It made it go faster. And then if we add the other one, here, we could do the same thing. So the CH3 could help stabilize. Right, and again, stabilized is activate. But if we had the meta, there is no way to get the methyl group next to the right. There's no stabilization because I can't get the positive. I can't get a resonance structure with the positive directly next to the electron donating group, right? So they can get hyperconjugation from the methyl to help stabilize that carbocation. So that's what we looked at on Tuesday. Now let's take a quick look at a deactivator, and then we're going to go through all of the activators and deactivators. Let's see if I put this in my notes the other day. So if we look at the nitro group, and now we can't do Friedel-Crafts, so we're not going to go the other way, but let's say we did bromination. So we see a little more than trace. We see small percentages, right? But in this case, it's our meta that is going to be our major product, and our ortho and our para that are going to be minor products. So again, the transition states can explain this. So going through the mechanism. So let's add the bromine. So we end up with that carbocation. Then that carbocation can rearrange. I'm going to try and slow down a little bit. I know there's a lot of drawing. Oops, I want to draw exactly the same thing. So we can get that positive there. But now if we think about that positive, I'm going to change it, the direction just a little bit. So I got the positive here. What's happening is that nitro group going to be stabilizing that positive? It's going to be taking some of that positive away from it, or is it destabilizing it? What's going to be the impact of this positive charge here with a positive right next to it? Good or bad? Bad, right? So this is going to destabilize this. Now that's slightly different than what we saw with the meta with the electron donating group with the alkyl, right? We didn't see destabilization, we saw what? No stabilization, right? Just had no impact because the positive is not in the right place. Here, if we have that positive there, what's happening to the reaction? I'm destabilizing it. When I destabilize that, what does that mean as far as the reaction rate? It's going to deactivate. Right? So that means it's going to slow it down. If we look at the meta, so now I add my bromine here, put our positive there, nitro is here. Now I can draw resonance contributors. And for this one, I'm going to go ahead and show you all of the resonance contributors. So you'll see I'm not lying to you. Be a horrible thing for an organic professor to do is lie to you. Okay, so we get this one right. The positive is not next to the positive on the nitrogen. We can draw another resonance contributor. And we get the positive at the bottom. Okay, so those are my three contributors. Is the positive next to the nitrogen positive in any of these? No, right? So therefore, this is not stabilized. It's not destabilized. It's just no stabilization, right? It's no real impact. So is it going to speed up the reaction? No, right? But then if we look at the para, we can draw a resonance contributor where we have those two nitrogens together. I mean, the two positives together. And again, because we have those two positives together, this is destabilizing. Right, and this is a deactivator. So if we looked at these, right, this is almost the inverse of what we saw for the electron donating group, the methyl, the alkyl group. Right here, we're not stabilizing, we're not speeding something up to get it to react. preferentially one position, we're doing what? We're deactivating the other two positions, leaving the meta as the only one left that's not deactivated. So if we look up here, what are we doing? We're saying ortho and para faster, right? What are we saying down here? Meta not any slower, right? Okay. So sometimes my son likes to race, right? Race, and sometimes he wins because he's the fastest, and sometimes he's the fastest because he's really getting after it, and sometimes he's the fastest because the other people just aren't as fast, right? So the way to think here is the meta won because it's just got the other people are just that much slower, right? Where up here, the ortho and meta won because they have the ortho and para won because they've been going much faster. Okay, that seems like I'm pushing this a lot, and the reason I am is this is important for you to understanding all of the activators and deactivators, right? Is that you understand these two processes, and there's going to be some reactions that will not work with some deactivators because they're going too slow, and there's going to be some reactions that are going to go more than twice because it's an activator. Now there's two parts of the activators and deactivators, and that's also the direction, right? So if we look at the direction group, directing effects, we can see that the CH3, and I don't know why I switched to purple, the CH3, right, directed ortho and para. If we look at the nitro, we can see that that is meta. All right, remember when we had directing effects of 1, 2, and 1, 4. 1, 2, right, was the kinetic product because it happened the fastest. It had the lowest energy of activation, and it happened the fastest. Why? Because of the proximity, right? I didn't have to do any orientations, didn't have to do anything. After I had my electrophile, the nucleophile was right there. The energy of activation was slow. So 1, 2 was always kinetic, right? But what about thermodynamic? Was thermodynamic always 1, 4? No, thermodynamic was the most stable product, right? So it could be 1, 4, but it also could be 1, 2. Same thing occurs with activating, deactivating, and directing effects, right? The activation and deactivation may be aligned with the ortho-para meta, but you can also have a deactivator that's also, so you may have an activator that is ortho-para, you may have a deactivator that is meta, but you can also have a deactivator that is ortho-para, right? So you gotta, now sometimes they align and sometimes they won't, right? So don't get into a trap of thinking that activators are always this and deactivators are always that. Because if you do, you'll get it wrong, right? So just like our kinetic and thermodynamic control, there's different reasons for both of those. The directing effects do have to be with the ability here, but that ability can change depending on a couple of factors. And to get into that, let's look at all of ours. So I'm gonna pull up a picture here. This is in your text. Make sure I downloaded it. Yep, there it is. Get it to a point where I can blow it up to where you can see it. Okay. So this is your big chart, right? And so you need to be familiar with this. Now it looks really complicated, and if you try to bulk memorize this, it will make your head smoke and give you troubles. But we'll go through each one of these categories so you'll see why it is, right? So we start at the top with activators. Okay, we have strong, moderate, and weak. If you're strong activators, right, also, right, happen to be ortho-para directors. Our moderate, notice that on our moderates, right, we still have something that has a lone pair next to it. So if you notice all of these, I have a lone pair that's right next to my ring, and we'll look at some resonance contributors so you can see why that's important. In this other one, we have something similar, right? But in these carbonyl cases, you'll see that they're going to be pulling electron density away from it because the carbonyl right there has a partial positive. Okay, so we're going to have some resonance contribution, but we also have a little less electron density. And we'll look at those. And then we have our alkyl. So R here is methyl, ethyl, propyl, all of those. Okay, and we'll look at each of these in detail. When we get to deactivators, notice that this first one is my halides. So a halide is a deactivator, but it's also what? It's an ortho-para director. What is different about a halide that might have it be a weak deactivator, but also an ortho-para director? What's the electronegativity of halides? It's pretty high, right? They're almost always going to be the one that's partially negative. Whatever's attached to them is going to be positive, right? So inductively, they have a very high electronegativity and a dipole. But what do they also have on them? Got a lone pair. What can a lone pair do? A lone pair can donate electrons back through resonance. So halides, and we'll look at this in detail, but halides have inductive effects that make it a deactivator, but resonance donation effects that makes it an ortho-para director. The next group is this moderate. Notice that they are all some type of carbonyl species, right? So we have the ketones, the aldehydes, the esters, the acids, the amides, we got the sulfonates, and then here we have the nitrile, which the nitrile is a carboxylic acid derivative with nitrogen on it, okay? And those are all meta-directors, okay? So our moderate, our meta-directors, and then our strong, the nitro, the ammonium, and then this trifluorinated species are all our meta-directors. All right, so let's start at the top and look and see what's happening with these. Okay, and for these, I'm just going to use the bromine. So it's going to favor ortho and para. So what I'd expect for my products are these two, right? The explanation for that is that if I show I'll draw the right thing. So here I have a bromine, right? I've got my hydrogen positive. Then what can happen is I can get my resonance contributor, right? This electron goes here, that electron goes there. That ends up giving me the positive right here. And now to stabilize that double bond, I have a lone pair, right? Can stabilize that positive. Now this is a strong activator because taking that lone pair and giving it that carbocation, what have I done? Do I have a carbocation anymore? No. The carbocation has an empty orbital. Does the oxygen have an empty orbital? No. So I've gone to a more stable species by going to this group, right? So if we look at this, right, we get our positive, right? That's the ortho position. And then we can delocalize to get this very stabilized species, right? So if we go up here, the oxygen has a lone pair, oxygen has a lone pair, nitrogen, 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 right? So they're all doing the same thing. Also, when we look at the dipole moment between the carbon and the oxygen and the carbon and the nitrogen, the carbon and the chlorine, right? What's happening with our dipole moment here? And I put them in the wrong order. So we can see, right, you got a dipole moment, getting a little bit bigger dipole moment, right? Much bigger dipole moment, because as we change the electronegativity of the other atom, right, we're pulling more electron density. So in oxygen and nitrogen, right, we have a small dipole moment. So therefore the resonance is the major impact. Questions about this one? And of course I could show the para would be the same thing, right? But if I do the meta, is the meta going to end up with the positive next to the group? No, right? So the reason the meta is not, let's go ahead and show that one. Right, if I had put the bromine here, get the positive, right? There's no way for me to there's no way for me to get the positive next to the oxygen. So if we look at the next group, so the moderate, again, we can get the ortho and the para as our major product. And around our room. And the reason for that one, again, is the intermediate. So we have our lone pair. So if we add our bromine here, we get this carbocation. And to save a little time, I'm going to show this lone pair going here, that pi bond going there, these electrons going here. So instead of showing it stepwise, I'm going to flip it all the way around. But then that gets me this. And now if we look at it, right, this is partially positive, right, partially negative. So that carbonyl, right, I could delocalize that carbonyl, but when I delocalize that carbonyl, the positive is on the carbon. So now what I have is I have a positive next to a positive, right? So although if we took this off, it would look just like our beginning. What happens now? Now it's deactivating, right? So that's why it's moderate and not strong, okay? Okay, so if we look at our class of moderates, anytime we have a carbonyl, anytime we have a lone pair right outside and a carbonyl attached to it, it's not. But why this one, right? Why is that one in the moderate? This has to do a little bit with geometry, right? So let's look at why the methoxy is there. Well, what happens when I have the oxygen up here and the CH3 here? Well, that doesn't look like much, does it? But does it look like much now? So that methyl group, right, is a tetrahedral. It's going to cause some issues. And what's the main issue that it's going to cause for this being as donating as the first strong activators? What happens if I have that big group? Well, I've got this group, right? What does that oxygen want to do? Does it want to be in line with that big methyl group, or does it want to be out of line? Which would be more favorable, being a little bit offline, right? Or being in line? So the conformation for this one is going to be eclipsed, right? So if I have my benzene in this direction, it's going to be here. And if that's not eclipsed, if it's staggered, what does it mean for the lone pairs? It means the lone pairs won't be as available, right? So the reason that the methoxy is in the moderate, not the strong, is because the sterics of that methyl group or ethyl group is keeping those from being planar, right? It's going to be tilted off. So it's a geometry problem. The last one, right, is the weak activator. And that's the one we saw here. And we'll still get the same directing effect. It's going to be an orthopara director. And if we draw our resonance contributor, again, I'm not going to show all the resonance contributors. I'm just going to show this one. And if we look at this one, how is this working? Well, we've got that p orbital. We've got that carbon. Can I do a full resonance with the methyl group? Is there a lone pair on the methyl group that allowed me to do a full resonance like I did up here? No. So how does this stabilize that? It stabilizes that under hyperconjugation. Okay, hyperconjugation is the same reason that a primary is less stable than a secondary carbocation that's less stable than a tertiary carbocation, right? We can get back donation through the sp3s hybridization orbital, right? But that's not going to be the same as a lone pair resonance. So therefore we can stabilize that carbocation, but we're not going to have the same level. So instead of being strong or moderate, we now get to weak. Still an orthopara director, still an activator, just hyperconjugation is not as strong as the full resonance. Okay. Question about that one? All right, so that's our activators. So strong activators, one more time. We've got oxygens and nitrogens with lone pairs, right? Either hydrogens or in the case of the nitrogen, positives, methyls on there. When we go to moderate, right, here we have the esters, we have our amides, right, and the methoxy. And then weak, we go to R, all of those are orthopara. So for activators, they're also all orthopara, right? Remember, they are separate, but this one's nice. All activators are orthopara. Okay, for the deactivators, let's start with the weak ones. Just keep going down. So that's my halides. Right, and that's going to be my halides. So HCl, HBr, I mean Cl, Br. And do they include fluorine on the chart? No, iodine. Fluorine is a bizarre. Carbon fluorine bonds are a little bit different. So if I had a bromine here, right, that's going to direct orthopara. Okay. Now, why is it a deactivator? It's a deactivator because the dipole moment is pulling electron density out of the ring. This is inductive. If we look at, so just right off the bat, it's pulling electron density out of the ring. So the nucleophilicity of that benzene ring is already decreased. So even before we get to the transition state, this is a less nucleophilic group because of that high inductive effect. When we look at our, and I'll put it back up here, if we look at our orthopara, we get our carbocation, and we'll show it delocalizing all the way around. So this goes there, that goes there. So if we look at our dipole, right, we've got a large dipole there. Is the bromine trying to make that positive charge more positive going to stabilize it? No, that's going to destabilize it. Okay, and if it destabilizes, what does that mean? That's a deactivator. So at this point, that is a deactivator. The inductive effect is causing it to be a deactivator. But let's redraw this here. So this is inductive. But if we redraw that molecule, now I have that bromine here, positive, lone pair, pi bonds, bromine, hydrogen. Now I've got these lone pairs. What can the lone pairs do? They can donate back to the ring. I can end up with the brominium ion. Have you seen a positive bromine before? Yes, right, we saw that previously. It has a directing effects with carbocations, and we saw brominium ions when we were doing bromination, right? So if we think about resonance, right? Resonance stabilizes ortho addition, right? It would also stabilize the para position. So we can show the lone pair coming here, electrons going around to that carbocation. So halides are deactivators because of their high dipole moment, right? So inductively they're deactivators, but by resonance they are orthoparadirectors, right? So that's why they fit into both camps. They've got such a large electronegativity that the inductive effect makes them deactivators, but they still have a lone pair like the oxygen, nitrogen above, so they are orthoparadirectors. This is the one you need to watch for, right? And what will happen if you're not careful with this is that you'll get all combobulated and you'll forget everything else, right? So think about lone pairs outside the ring, right, are orthoparadirectors. If it can donate electron density, then it is an activator. If it is pulling electron density, then it is a deactivator. Those are two different reasons, right? This has a lone pair right out the ring. It is an orthoparadirector. Okay. Questions about halides? I'm taking a lot of time on this. Two reasons. One, this ends up being a huge problem year in and year out. And second, somebody told me this week I was going way too fast. So we're slowing down just a little bit. So let's look at the next one, moderate. The moderate, notice we have carbonyls on all of those. So let's look and see what's happening with moderate ones. And this one's going to be a meta director. So the major product we're getting out is meta. First, if we look at the resonance contributor, we can see that that's going to pull electron density out of that ring. So it's going to decrease its nucleophilicity. We see why it's a meta director. We don't want to have that positive next to the ring. Right, and so the meta will not allow that positive to be next to the ring. The ortho and para would be. So this is the same as what we saw before. And again, the reason that we don't want the positive right next to the ring is because that carbonyl will have that type of species. Okay, when we look at strong deactivators, and in this case, what we have outside the ring, and we've already done this one, so I'm not going to go, but the thing to think about is that when we show that nitrogen, we don't have to show the resonance contributor that nitrogen is positive, right? So it's going to be pulling that negative charge towards itself, or that electron density towards itself. So if we think about our deactivators, right? The weak deactivator is just an inductive effect, right? Just an inductive effect, no possibility of a positive charge. In fact, if I can delocalize, that gives me a resonance stabilization, right? So it's just inductive. If we look at our meta directors, what's going on there? The resonance contributor of that carbonyl gives me a positive, which means really I'm looking at a partial positive. So I've gone from a inductive effect from the atom to a partial positive charge from the resonance contributor. And then when I go to strong deactivators, what do I have right outside the ring? A positive, always a positive, right? So if we look up here in our chart, notice that the nitro group's not shown, but the nitrogen, right? The nitro group does have a positive, but you have to show it. But this ammonium, right, has it. Now this one is a huge inductive effect. You're not going to see that too often, but again, if you see the trifluoro, it's going to be a large deactivating group. Okay. Questions about this? Yes, sir. Well, except for this trifluorocarbon species. Yeah. But the nitrogen positive, the nitrogen. If we look at Friedel-Crafts alkylation, remember Friedel-Crafts alkylation won't work with strong deactivators. What is that? That's this group, right? So if I want to do Friedel-Crafts alkylation, it won't work with the nitro or the ammonium salt or the halide, the trihalide, okay? All right, so we got all that. How is this going to be presented? Well, it could be easy, right? Like, tell me whether it's a deactivator and an activator. So let's look at a few of those. So activator, deactivator. One question, ortho, para, or meta, okay? So let's take a little time. I'll draw the structure, and then you tell me whether it's an activator, deactivator, and whether it is a ortho or para director. On this first one, feel free to go back to the chart, but we're going to do another set and I'm going to ask you not to look at the chart. And now that you have it written down, I'll go show you the chart. I just realized y'all probably don't have the chart. So there's the chart. Okay, let's go look. So how I would answer these, right, is, okay, first one, does it have a lone pair right outside the ring? Well, yes, it does. If it has a lone pair right outside the ring, what is it as far as directing effect? Ortho pair, right? Is it oxygen and nitrogen right outside the ring? Yes, then it's an activator. Oh, and nitrogen, that's not positive, right? So oxygen, no problem. Nitrogen, that's not positive. That's a lone pair. Right? So that's an activator. For bonus, is this strong or weak? Strong, moderate, or weak? So this one's a strong one, right? The next one, do we have a lone pair right outside the ring? Yes. So this is an ortho paradirector. Is it going to be an activator? Is it a nitrogen or oxygen? A nitrogen that's not positive right outside the ring? Yes, right? I could also say carbon, right? So carbon, nitrogen, oxygen, where the not or and the nitrogen is not positive, right? That's going to be an activator, right? And in this case, how do I know if it's moderate or strong? The carbonyl, right? So the carbonyl attached to the nitrogen makes this moderate. And we'll see where the difference between strong and moderate comes up later in the chapter. Okay. The last one, do we have a lone pair right outside the ring? No, we have a carbonyl carbon, right? So all of a sudden, since it doesn't have that lone pair, that should head me to be thinking about it not being an orthopara. What do I see as far as the dipole moment right outside the ring? I see a positive, right? If you see that partial positive positive, that should head you towards meta, right? Since it has a positive here, what does that mean as far as activator, deactivator? Okay. So deactivator, right? So it's a deactivator. Is it a halide? No. So therefore it is a meta. So what you can get to on these is start asking yourself a set of questions, right? And in this one, again, this one is, if it's got a full positive, it's going to be strong. So this one's going to be moderate. Okay, let's look at another set, same 3 questions. This one, I'm not going to give you the chart. See how you can do. Without the chart. Okay, let's take a look. This first one, this is toluene. Is there a lone pair in the benzylic position or outside the ring, right? Is there a lone pair in the benzylic? No. So it's not a given orthopara. So let's go back. Is it going to be electron donating or electron withdrawing? Right? Does it have a partial positive or a positive right outside the ring? Right? No. Could it contribute electron density to the ring? Yes. How? Hyperconjugation, right? So therefore, this is going to be an activator, right? And all activators are orthopara. On the second one, does it have a lone pair in the benzylic position? No. So I need to look back over the activator deactivator. Does it have the ability to donate electron density, or is it going to be pulling electron density? Well, it's got a positive charge, so it's going to pull electron density, pulling electron density, partial positive and positives. That's going to be a deactivator, right? Deactivators that are not halides are what? Meta. The last one, we have a halide. Does it have benzylic lone pairs? Yes, it has benzylic lone pairs. So therefore it is an orthopara director. Now, is it going to donate electron density or pull electron density? It's going to pull electron density. How? Inductive. So this is a deactivator. If we go back up here and add the strong and the weak, a strong, moderate, and weak, right? The methyl is going to be weak, right? The positive charge is going to be strong. And the halide, the inductive effect here is going to be weak. Okay, so if we think about our weak activator, it's just hyperconjugation. If we think about our weak deactivator, it's just inductive. Okay. Okay, so what does this mean as far as life, the universe, and everything? Well, what it means is that I can predict the products if there is already one group attached. Both of these are nitrations. Both are going to add NO2. In this case, I have a methyl group, right, which is an alkyl group. Those are orthopara directors. So therefore, my products are going to be ortho and para. On the second one, I have this carbonyl. Remember, that's partial positive. That partial positive should tell me this is a deactivator. It's a deactivator, and is it a halide? No. So therefore, it's going to be a meta director. All right. Since it's a meta director, I'd expect my product here. Again, you need to know what the reactions are, right? But that's going to give me the meta product. So what we've added now is a level. So we've got regioselectivity based on the first group that's on there. Notice it's the methyl that directs the nitro. Okay, one of the things that students can get backwards is, what is the directing effect of a nitro? Nitro is a strong withdrawing group. It is a meta director. What do you think students do as a mistake? Instead of looking at the group that's attached, they look at the group that is being added. The group that is attached directs the group that's being added. The group that's being added has no control over where it's going to be added, right? So don't look at the final product, the nitro, and say, well, the nitro is metal, I should add it. No, no. The toluene is already attached. It has control, right? So it's an orthopara director. The meta is going to add orthopara. And the second one, right, we have a meta. Both of these can add, right? Now, as far as which of these two reactions would occur faster, which one's going to occur faster? The first one or the second one? The first, why? It's an activator, right? So it's activating. It chooses orthopara because orthopara is more stable. That means it's going to have a lower energy of activation. It's going to go faster. The second one is a meta, not because the meta is destabilized, but the meta is not stabilized, right? And I'm pulling electron density away from that ring with that partial positive. So therefore, deactivators go slower than activators. That's going to be important when we look on Monday, okay? All right, let's look at a few practice problems. Let's try this. So do some nomenclature. Get y'all ready for the quiz. If you have time to do it, yeah. So we'll be using common and IUPAC. So the question will be very specific. Okay, so let's take a look. What's the common name for the first one that's also an accepted IUPAC name? Toluene. I could have also named this as what? Methylbenzene. Okay, the second one, common, aniline. Okay. That can also be known as aminobenzene. Last one, this one sometimes people forget. Anisole, right? That would be methoxy benzene. And if we look at this one, we could call this para-chlorotoluene, right? Or it could be known as 1-chloro-4-methyl-benzene. Why does the one go with the chloro and not the methyl? Alphabetic, right? And then this one here could be known as paraxylene. This is not a common name I expect you to know, but you'll see it. Xylene is 2 methyl groups, so paraxylene. Most often you'll see this one as 1,4-dimethyl-benzene. You almost never see this one, although practically it's not incorrect, but you'll almost never see this one as methyltoluene, right? Because if you're going to use the common name, you'll use xylene, not toluene. So this would be dimethylbenzene. Okay. So if this surprised you, remember this could be on the quiz, so go take a look at it. Okay, let's jump back a little bit. Let's draw some more molecular orbitals. Okay. Draw me the 4 molecular orbitals for 1,3-butadiene. because of time and I want to get one more question in. Let's go ahead and put these in. So we're looking for the p orbitals. So we have 4 p orbitals. And in Psi1, those are all in phase, right? There's no nodes. And Psi2, how many nodes do we have? 1, right? So we put the shading on top and the bottom. Psi3, we're going to have 2 nodes. So we can shade this way, giving us 2 nodes. And then 4, we're going to end up with 3 nodes. So none of the pi bonds, p orbitals are communicating with each other. Which one's the lowest energy, Psi1 or Psi4? Psi4. So the lowest energy is all in phase. They're all communicating. The highest energy is 4. None of them are communicating. Any questions about this one? Again, we can use the kind of string, you know, 0 node, 1 node, 2 nodes. If you had to do 6, right, you could just keep going up and just adding nodes between those. Okay. Your lowest is all in communication, highest is no communication. Okay. Let's do a retro Diels-Alder. There were some students that were having some problems. So if I was going to create let's redraw this a little bit. Okay, so give me the 2 starting materials that would create this Diels-Alder product. Okay, we're out of time, so let's go ahead and take a look. So in this case, I'm going to go directly across from that double bond. I'm going to break here and there. This is the favored product because it's going to give me this diene, right? And it's going to give me, now there's a double bond there, so I'm going to have to use a triple bond. And I've got the dihalide here. Okay. That would be the favored one, because if we had done it the other way, we would have ended up with this. And remember that we want electron withdrawing groups on our dienophile, right? So this would not be the favored product. The favored product would be the first set. All right, so see y'all on Tuesday. The quiz will be up in about 15 minutes, but you have until 10 o'clock to finish it.